Hello, everyone. I'm AI Voice on behalf of Teng, who comes from the University of Alberta in Canada. I am very glad to share my research work here. The title of this presentation is Point-Based 3D Virtual Fixture Generating Method for Image-Guided and Robot-Assisted Surgery in Orthopedics. This presentation includes 7 parts. Number 0 is a brief introduction about what is virtual fixture. Number 1 is related works. Number 2 is background and motivation. Number 3 is our proposed solution. Number 4, simulations and experiments. Number 5, limitations. Number 6, summary and conclusion. First of all, what is virtual fixture, VF? A simple example of VF is a virtual wall. So, what is virtual wall? Let's watch this demo video. This video demonstrates a virtual wall box test using a 3DOF robot. As we can see in the video, there is a virtual box shown on the left-hand side while a user is operating a 3DOF robot on the right-hand side. The user is holding with the robot end effector and tries to touch the virtual walls from inside of the virtual box, left, right, up, down, back, front. And the virtual walls will provide resistant forces which will be delivered to the user via the robot. The resistant forces are represented by the progress bars of X, Y, and Z in the video. In units of Newton, the user can feel all the faces and edges of the virtual box using the robot. Note that, in this video, the VF, i.e., the virtual walls, prevents the robot end effector from going outside of the virtual box. As we can see from this example, the virtual fixture is a virtual box while the virtual box is composed of 6 virtual walls. These virtual walls are simple planes, and easy to be expressed by math equations. Therefore, they are relatively easy to be set up based on the math equations. Here are some related works about virtual fixture. Virtual fixture, VF, is initially proposed by Rosenberg in 1993 in aiming to help operators to achieve better performance in teleoperation tasks like peg-in-hole. In the beginning, the VFs were generated from simple regular shapes, such as a planar, a sphere, or the virtual box we saw in the video. Those VFs are relatively easy to be generated by using their mathematical equations. For other VFs with irregular shapes, VFs generating could be a challenge. To solve this problem, Zills and Salisbury developed a God-object algorithm, which can generate VFs for objects with complex shapes like this space shuttle. This algorithm requires a triangle meshed model of the object. Kapoor and his colleagues presented a constrained optimization framework for generating VF, by assembling task primitives in a predefined VF library. Around this constraint optimization method, they applied it to various applications in surgery, for example, knot positioning by using multi-robots. This constraint optimization method requires knowing the geometric constraints and robot kinematics. Ryden and his colleagues developed a method of generating VF from point cloud to protect the beating heart during surgery. Here is the background and motivation of this work. In robot-assisted surgeries, virtual fixture, VF, has been serving as a vital role, such as guiding surgical tools movement and protecting a beating heart. In orthopedic surgery, preplanned images are often used in the operating room, on which some curves might be drawn. For instance, to mark out the boundaries for osteophytes to be removed. These curves can be used to generate VF to assist in removing osteophytes during the operation. A main challenge is that the hand-drawn curves or surfaces usually have an irregular shape, as shown in this figure, and usually they cannot be mathematically represented by equations. Motivated by this challenge and inspired by Ryden's work, an adapted algorithm of point-based 3D VF generating method is presented in this study. With this method, the VF can be generated directly from cloud points, no matter the point cloud is with regular or non-regular shapes. Here are the three key parameters used in the algorithm. The first key parameter is the p/h/IP, where h/IP is the haptic interface point, also equivalent to the robot end effector. The second key parameter is the p-proxy, which is the virtual avatar of the h/IP point. The third one is the small p/I, which is a single point in the point cloud. Based on the relative positions of these three key parameters, the VF algorithm is developed, as illustrated in the right-hand side figure. For the complete algorithm and detailed explanations, please see our paper for details. To evaluate the effectiveness of the presented VF algorithm, a series of simulations and experiments are conducted. For the simulations, there are 4 scenarios are considered, that is a single point, a line segment, a 2D teapot, and a 2D hand-drawn omega symbol from an image. In the simulations, we evaluate the algorithm and observe whether the proxy and the normal vector behave as expected. Note that in the figures, the proxy is represented by the center of the red circles while the normal vector is represented by the magenta arrows. The results show that the effectiveness of the VF algorithm on various geometric entities is well demonstrated by the simulations. And the VF algorithm is valid not only for point cloud with regular shapes, for instance, the single point and the line segment, but also for that with freestyle non-regular shapes, for instance, the 2D teapot and the hand-drawn omega symbol. There are 2 experiments designed in this work. In experiment 1, a set of point cloud in 2D square shape is used. The point cloud is generated in a specific area in the robot base frame. About 40,000 points are generated. During the experiment, the user moves the robot end effector to probe both sides of the VF generated from the point cloud, as illustrated in the top figure. And the VF force is rendered accordingly and delivered to the user via the robot. The results show that the VF force is appropriately rendered on both sides of the square point cloud, which indicates that the VF algorithm is effective in 3D space. In experiment 2, the VF is evaluated in an image-based scenario. First, a preplanned image is obtained, as shown in this figure, A. Next, the hand-drawn curves are extracted by using image processing techniques. Based on the extracted curves, a set of point cloud of the curves is obtained. Then, the point cloud is registered into the robot base frame, as shown in the figure, C. Figure D is an enlarged view of the point cloud. The results demonstrate that the VF can be generated based on a hand-drawn curve from an image, while the VF force can be appropriately rendered in 3D space. This is a demo video of all the simulations and experiments just presented. There are some limitations in this work. One limitation is that the quality of visualization can be improved. In the experiments of this work, only the point cloud and the robot end effector, i.e., the HIP, is visualized on a monitor during the task. In future work, all key virtual fixture features, for example, proxy point, contacting region, and normal vector, in 3D space will be visualized by using the augmented reality AR technique, which can better help the surgeons to utilize the virtual fixture. Another limitation is that experiments in a more real surgery scenario are necessary. In this work, we employed a simplified surgery scenario, that is a 2D bone in an image, to evaluate the effectiveness of the VF algorithm in 3D space. In future work, we will conduct experiments in a more realistic scenario, for example, using 3D printed bone and real surgical tools to perform some surgical procedures with the help of the virtual fixture. Lastly, summary and conclusion. In this work, an algorithm of point-based 3D virtual fixture generating method is presented, which allows to generate VF directly from point cloud data where the point cloud can be in any regular or non-regular shape. A set of simulations and experiments demonstrated the effectiveness of the algorithm. The experiment in an image-based scenario demonstrated the capability of the algorithm to generate VF for hand-drawn curves in a preplanned image, thus demonstrating that the algorithm is promising to be used in image-based and robot-assisted orthopedic surgeries. At the end, I would like to thank my supervisor Dr. Tavakoli, and all the members in the TBS lab group, as well as the funding sources. That is all my presentation. Thanks for your attention.